the same theory you just heard about, but from a fundamentally different perspective. While John was talking, spoilers. While John was talking about some mesons, which are some flux tubes with boundaries, I'm going to talk about things that I interpret as interfaces, which have no boundaries at all. While he was using S-matrix Bootstrap to try to understand this problem, I'm using Monte Carlo to get these numeric values for these coefficients for the different theories. This is work in progress that I hope it's going to be out soon, but there are still some wrinkles that we need to figure out before that, especially related with the breaking of integrability for these the strings. So if anyone knows how to identify properly from the partition function perspective, that would be very nice. So the motivation is a bit, as you heard before, there are these flux tubes. We really don't know to describe them from a fundamental theory. So maybe a good starting step is just to assume they exist and try to understand what are the possible dynamics that these objects have. This has been working procedures for a very long time, and people have come with a very synthesized effective theory. But if you look into the literature, there are tens of papers that step by step show that order by order in some expansion, the coefficients are universal and couldn't be anything else besides you get from Navigato. And the status is that the leading coefficient that you can have in this expansion is this extrinsic curvature into the form. From the Bootstrap perspective, the only thing we have is this bound that the geometry, well, you have bounds on higher coefficients, but for geometry, we just have this. So it's also interesting to try to find some theory that saturates this bound. And what I'm trying to convince you today is that the Ising is a theory that if it doesn't saturate the bond, it's very close from saturating. It's 3 years. Okay, so the setup is the following. Most of the work that has been done in this effective string theory is about finding the low-lying spectrum of the theory, is about this 1D perspective where the string with some excitations that can scatter in each other. But I need to extend this effective action to a full interface. So the first thing I will do is just to basically finish the computations that have been done before in this theory, but instead of taking the limit where one of the sides of the string is long, I need to take the limit where the area of the world sheet is large. Then I'll discuss a bit the Monte Carlo setup. How can we realize an interface that is described by this effective string theory in the 3D Ising? And finally, I'll conclude with the integral results. So the most natural description of these flux tubes is an effective field theory, which in the static cage has this expansion in 1 over the area of this interface, where all these terms are model independent, and this is the first term that is not fully fixed. So we call the first part the universal contribution, and we call this one, this thing multiplying geometry, the non-universal one. This is a very nice framework to compute the first leading correction in geometry to the partition function. But as you can see, if I want to compute the partition function 1 over area to the cube with all these operators, I'm going to spend a lot of time doing computations which are not that easy. But it's great to compute, so as I said, it's very good to compute the first non-universal correction to the partition function, which for finite interfaces has this expression here with this Eisenstein series. This requires the regularization of some Eisenstein-like series that has been done for this particular case, has been done in 83 by Leeds and Field. And this reduces to the TVA result when you take the ground state limit of this free energy. So in order to compute the universal corrections, there is a nicer framework. This computation was firstly done by Below, Kazel, and Ferrer in 2006, where they go to the Polyakov formalism of this Navigato, and there's the integrate. You just compute this partition function. This is kind of technical computation, but they come up with this very nice result. And they tell us a way of expanding this in 1 over the area to whatever order we want to compute. I want to highlight a bit this factor of square root of 2 pi, because there is a kind of open question, at least more on the lattice side of this debate, which is that the EST does not predict the normalization of the partition function. But one of the things I'll try to convince you of is that we think it actually does. There's just some issue here that is not properly understood, or maybe just some typo in the computations. Okay. So you can do the free energy expansion for that. You get all the terms. It's just a bunch of Eisenstein series. It's not particularly nice. And there is also a limitation that this expression has not been derived for a generic torus. It's only been derived for a torus with no twists. So one of the things we are also going to do is to generalize this for the most general torus you can have, which is when you have other twists. To do that, we needed to kind of introduce some new paradigm, because you see, from this perspective, it's not very easy to see how I could add the geometry there at the starting point. Maybe if I knew with the theory that has geometry, it is exactly, I could plug it in, go to this computation, and get the corrections to this partition function. So we come up with a slightly simpler framework, which also allows us to leverage integrability, or at least the low energy integrability of the flux tube, which is to consider this string like as a one-dimensional object with some internal degrees of freedom, whose like rest mass is given by whatever are the excitations it has, and then it can propagate in the transverse direction with some momentum pz. You can integrate the momentum, and you get some expression like this, which is analogous to the one they have, where we now can just plug in whatever spectrum we get for the flux tube, for example, coming from TBA. And this is one of the things that is still not finished, is to do the full TBA for the full spectrum of this string when we have geometry to the S matrix, and see what you get for this expansion. But this also already has a very convenient advantage, is that now we can add the twist by just inserting some shift in the momentum when we glue the partition function. So we can generalize the previous results already for the twist case, and we have this. We also have, as I pointed out, a different normalization for the partition function. The difference of normalization will reflect in the area independent term of the free energy. So this is this -1 log 2 pi shouldn't be that. Okay, so now that I have some predictions, I can go to the lattice and I can actually test all these predictions, and hopefully I can measure the geometry.
I couldn't tell the difference between what causality law and the what you are doing.
So here they start with the Polyakov action. They have some doses, and they compute everything. Right?
I don't know. The one of this no.
And they just go through this brute force computation where they integrate over the modular space of the string. What I'm saying is just there is one object with some internal degrees of freedom, like an hydrogen atom. Right? And this object can have momentum in the transverse directions. And the result is basically the same. Actually, the other thing they do is that this spectrum both the spectrum and these degeneracies come out of their computation and not plug in by hand. I'm taking a different perspective where I can get access to the spectrum from some other way, for example, using TBA. And then I compute the partition functions. They are doing something a bit more hardcore.
I guess what confuses me is that you're talking about TBA, but I mean, TBA applies to integrable
Yeah,
theories and complex strings are not integrable.
but the low energy sector is supposed to be approximately integral. Then there is a question of when do I lose integrability in this 1 over the area expansion? This is a thing we haven't fully figured out. That's why I don't have, and I'm not showing any results with TBA for this partition function. If you have questions, please go ahead and ask them. Especially because I may forget to mention something important, and this way you remind me. Okay, so we have prediction. We fully generalize, we generalize this computation, especially the geometry computation, to a finite interface, which has not been done before, and we potentially fixed a long-standing issue in the lattice community, which was this normalization of partition function that people up to now have been fitting. And I think this normalization might also be part of the reason why people have been looking more to the spectrum of strings instead of looking the spectrum of the spectrum taken from the Polyakov correlators, rather than just looking at interfaces. Okay, so the question is now, how can we realize one of these? And the idea is basically the same. You go to the simplest model you have, and you do the simulations there. So this is not new. This has been done in the lattice. This kind of interface study has been done in the lattice community for a very long time. The novelty here is that we can actually reach such a high level of precision that we can measure geometry from this. So the setup is the following. We have some 3D Ising. We put anti-periodic boundary conditions in one of the directions. Actually, how am I doing it?
20 minutes.
20 minutes still.
Plus questions.
Okay. So we put anti-periodic boundary conditions in one of the directions, and this will force that somewhere in the middle there is a region where the spins are anti-aligned. Now, if I'm near the critical point where the correlation length on the lattice is very long and I recover the continuous symmetries, whatever is the theory that describes this interface needs to be at leading order to the effective string. Right. So there is also kind of an, well, maybe just confusion on my part on this perspective. This interface melts when we reach the critical point. So it's not clear. There's something that I like to do, but it's not clear how to do it. How to describe this interface from the CFT perspective of this model. Good. But that's an open question for me, at least. So the way we do it is we use some Monte Carlo to measure this free energy. Sorry. And now, from the Monte Carlo perspective, there's a limitation here is that we cannot really measure partition functions directly. We cannot control the normalization that Monte Carlo gives. So we need to extend the system, the configuration space, such that both the traditional Ising spins and the couplings on some plane are free variables that are updated with some Monte Carlo dynamic. And then there are methods that allows us to estimate the ratio between the partition functions, between the partition function of the interface of the partition function of the Ising with periodic boundary conditions and the partition function of the Ising with anti-periodic boundary conditions. And the only thing between these two systems is that there is an interface somewhere in the middle, right? Whatever is the bulk dynamics, it will be the same in these two systems. So that part of the free energy factor out, and we can isolate the contribution to the free energy coming just from this interface. Okay, is any questions about the validity of the Monte Carlo setup to study this effective string theory?
How do you compute this issue?
All right, so that's the next slide. So the way we compute this ratio is well, it's, if you know it, you know it. If you don't know it, I don't have time to explain it. It's a multi-canonical method. And what this does is basically allows us to estimate some entropy or generalized entropy, or in this case, actually the free energy of the model of the system with some couplings J in the boundary. And from that, we can just extract the free energy. So I just want to point out something here that was kind of relevant for, or that enabled us to actually achieve this high precision, is that we divided these weights into two parts: a continuous part that is very easy to estimate, and then a discrete part that's where all the fine detailed information about this model is. That in this case, since they are separated by 2 orders of magnitude, really sped up this multi-canonical method using the Yang and algorithms. Okay, so these are the raw results. These are the results for all the areas and all the transverse volumes we studied. These are only for square lattices. So not for square lattices, for square interfaces. And this LZ is a transverse volume. So you should imagine this as I have some finite interface and I make the transverse direction longer and longer. And so there are 2 regions in this plot here. There's this finite LZ region, which I'm not going to discuss too much about today, but these basically allow us to go beyond the AST to extract some more information than just the effective string theory. If you want to hear about that, invite me some other talk. We're just going to focus about this region where the results become independent of the transverse volume. This is the region we're going to use to extract this geometry information. So you can kind of average over the transverse volumes to the right of that region, and you get some free energy as a function of the area. You have a nice clean linear behavior. This is important because we need to be able to extract the string tension with a high degree of precision, which in this case we were able to reach like 10 to the minus 6 relative precision. And then the geometry corrections are in the small deviations between the Monte Carlo data as the balls there and the dashed lines. So these geometry corrections are really, really small. So the next step before we can go to geometry is to try to answer this question: if the constant term is a parameter we need to fit or not, or if it's predicted by this computation. And if you subtract the linear term from the free energy, you see that it goes exactly to the result we predicted. This 1/2 log of 2 pi is around 1. So you see that in this scale, there is no way that that's compatible with the results. And you can start to see this at the geometry corrections as the little deviations that appear in that region. Well, very close for very small lattice, or for very small areas, very close to the Avogadro phase transition. Okay.
So what are those no corrections again?
Sorry?
I mean,
This is the geometry. So this is the universal part. This is the Lambo-Goto contribution to the partition function. And you see here, there is a region where it deviates from the linear behavior. That's some, here is where the Lambo-Goto contribution is loving it. And then here is where you see the geometry appear.
So geometry is splitting between the blue dots and the dashed.
Yes.
What? What about the correct? I mean, how are you gonna disentangle geometry from gamma 5, gamma 7?
So gamma 5 appears at so this gamma 3 is 1 over area cube. Gamma 5 appears at 1 over area to the fifth, right? So that's also something that we are hopeful that the TBA can help us with, because if I can get a TBA spectrum for all the excited states, I can just plug it in and get all these corrections, whatever order I desire, until integrability is broken. That's why it's still a bit work in progress, because so we studied the effects of these subliving terms without knowing what they are. If we can have them, we'll be able to extract a little bit more information. So this is, so what we've done here is to get the raw Monte Carlo data. We fit for the string tension using this large area behavior. And we know the result for the coefficient multiplying gamma 3 for square interfaces. Just gives you these numbers here. And so this is kind of a lattice, direct lattice measurement of minus gamma 3. It's important because gamma 3 will be negative in this case. And so the left hand is good to messy. It's a very small effect, but you can see that you can maybe be a bit skeptical, but it kind of plateaus in some for some value. These different colors are just different temperatures, like by that I mean just different distance to the critical point of the 3D icing, because ideally I'll go as close as the 3D icing critical point as I can, but then correlation limits become very large, and I need huge lattice volumes to be able to measure it. This is the main difficulty here. So what we did is we simulate a bit further away from the critical point, and then try to extrapolate to the critical point. And this is that extrapolation. So there are many fits here because I have some trust issues with fits. So I try to make it as robust as possible. By that I mean I try to vary the range that is in the fit. I try to add more subleading terms to see if those subleading terms will change the value of gamma 3. But the important point here is the following. Being closer to the critical point, this t equals 0, seems to bring gamma 3 closer to the bootstrap bound, seems to make it more negative. And adding subleading corrections, which is this green, this gray out green data. So that's what happens when I try to add for 1 over a to the 4. Also contribute to bring the value of gamma 3 down. So we are kind of cautiously optimistic that whatever the right value is somewhere in this shaded region, much closer to the bootstrap bounds than previous estimates. Okay, this is mostly it. But I can maybe also talk about this. This is already a bit outside the scope of the EST, but we kind of observe this kind of universal behavior for the thing I'm calling here effective string tension. So the effective string tension is defined both in the limited area of the interface is large and the limit where the transverse volume is large, but we can also play this game of studying the string tension when the transverse volume is large. And after you rescale the numeric data by the mass of the lightest glue ball and the string tension, you see that all these curves for all these different temperatures close to the critical point collapse into each other. This is the original data. And so now we are trying to figure out what this can tell us about this EST and maybe some things beyond just the EST.
I have like a general question. So how did the value of gamma 3 is so close to the bound, which is surveyed by the model of logic of this CTP factorless matrix? What does it physically mean? Because we'd expect it for icing, we have a lot of particle production, there would be like a glue ball mixing.
Yeah, I don't know.
Isn't it a bit
maybe we should discuss that.
okay. Okay, there are no more questions. Let's thank the question saying. Poi abbiamo matrice, esatto, questa immagine che Related to the same as integra continui, it means that the factor production inside that power loss at rest is or it's very small.
From that we learned that like on the like what the fun is it like always that's fun like when I did
Okay.